It hugs the ground at nearly 500 miles an hour. From over 1,500 miles away, it can hit a target within 10 yards. It can seek out and destroy the enemy without a pilot. The missile is a crushing weapon of choice for today's battlefield. Baghdad, 1991. The Tomahawk has its baptism of fire. Wave after wave of cruise missiles hit their targets.
There we go. Yes, the latest Tomahawk cruise missile to fly just over our position here.
Operation Desert Storm catapulted the Tomahawk onto the world stage. A smart flying bomb that struck with awesome precision. But the cruise missile hasn't always been the general's silver bullet. It took engineers decades to get it right. To build such a weapon, they had to overcome a series of extreme technical challenges. What does it take to push a 1.5-ton missile out of the ocean? Fly it at 550 miles an hour for 1,500 miles, dodging enemy radar, and then home in on its target to strike with deadly accuracy?
Tell me when you think it's getting close.
It's getting close. It's getting close. It's getting close.
The first challenge: firing a missile that weighs as much as a family sedan from a submarine underwater. With Tomahawks on board, a submarine turns from an underwater weapon to a global player.
The range of the weapon is considerable. The cruise missile now allows us to target the population centers for 90% of the world's population.
Action stations, action stations, action stations, TDAM engagement. All compartments, check communications, all compartments, check communications, DCHQ.
Captain FCO.
Captain.
The TLAM weapon system is in weapon ready state 1.
Today, a sub can simply fire and forget, safely hidden beneath the ocean.
Firing order will be 1, 2, 3, then 4 tubes. Salvo duration will be 6 minutes.
In the 1950s, the Navy could only fire missiles from the deck of submarines, an extremely awkward maneuver.
To meet the fourth missile type, whose mission takes it from surface to surface, we go to sea to rendezvous with the submarine.
The sub had to break cover and surface so the crew could fuel the missile and assemble launch equipment, leaving the sub exposed and vulnerable. The Navy desperately wanted to launch while the sub was underwater. But there was a problem. Firing a missile in a confined space creates an explosion so violent it rips a submarine apart. Navy engineers came up with an ingenious solution. First, flush the missile out of the torpedo tube with a jet of water. Once outside, fire the missile's rocket engine clear of the submarine.
Weapon system ready. Allow fire.
This is how they still launch the Tomahawk today.
Execute initiated. Time of launch in 5, 4, 3, 2, 1. Initiate execute. Smack's correct. Discharge correct 4 tube. Salvo complete.
The Tomahawk's rocket booster weighs only 600 pounds, but accelerates the weapon up to 50 miles an hour underwater.
Missile broached.
It burns for only 12 seconds, but catapults the missile just over 1,000 feet into the air.
Booster separation.
The Tomahawk's booster may look low-tech, but making this rocket engine safe enough for a submarine is a triumph of modern chemistry. Most rockets are powered by liquid fuel. Two different liquids are fed into a chamber where they ignite and drive the rocket. It's powerful, but dangerous. To show the hazards of liquid fuel, chemist Sidney Alford will replicate a German fuel recipe from World War II. He will inject two liquids, hydrogen peroxide and hydrazine, into a miniature rocket motor.
Please stop panicking if anyone is thinking of doing so. Here we go.
The two fluids simply have to touch each other to combust spontaneously.
That, I think you'll agree, is a pretty violent, indeed explosive reaction. No particularly luminous flame, but the sound alone indicates that it's very, very violent. I'm just going to wash my face slightly. I feel slightly squirted on the head. There we are.
And Alford only used a few drops of each liquid. But the components are dangerous even before they are mixed.
Each of them is not a very nice chemical to have around in its own right. Hydrogen peroxide, if it's very concentrated, can actually detonate. If it gets spilt onto inflammable materials like cotton or paper, tends to catch fire spontaneously, not what you want in a submarine.
For many in the Navy, the thought of putting liquid-fueled missiles on submarines was shocking.
I've been told that the submarine captains blanched at the idea. They thought it was an awful idea.
There was only one alternative: solid fuels, like gunpowder. They were safer, but far too weak to lift a large missile out of the ocean. Solid fuel needed a big boost. This challenge landed on the desks of Charles Henderson and Keith Rumble. They had to find a chemical that made solid rocket motors burn hotter and create more thrust.
We looked at additives that we could put into the solid propellant that would increase the heat of combustion. And we're going through the periodic table.
After testing many different chemical elements, they zeroed in on the ideal candidate: aluminum. When pulverized, this metal burns easily at 2/3 the temperature of the sun. Unfortunately, the more aluminum they put into their motors, the less potent they became. Finally, Charles Henderson found a way of squeezing 20% aluminum into a rocket engine, but only theoretically. Would it work on an actual rocket? Physicist Rob O'Brien is crazy about rockets. He will demonstrate the explosive effect of Rumble and Henderson's formula. O'Brien has mounted small rocket motors upside down on electronic scales. This allows him to measure the force each one generates. A simple gunpowder motor compared to an aluminum motor.
3, 2, 1. 3, 2, 1. Ignition.
Gunpowder produces about 1 kilogram of thrust. The aluminum motor generates twice as much.
Well, in terms of a rocket motor, if you want a high thrust, you really want a high velocity exhaust. So in order to get that, you would increase your temperature of the burn. And so putting aluminium in your mixture of the fuel increases the temperature. And if you increase the temperature of the burn, you can increase your thrust quite dramatically.
Now O'Brien will put these motors to the ultimate test. He will strap them to one of his rockets. First, the gunpowder. gunpowder is so weak it doesn't even tickle the rocket. Now, the aluminum.
Seven, 6, 5, 4, 3, 2, 1, ignition.
In the 1950s, Rumble and Henderson's improved booster was a quantum leap in missile technology.
Well, it was great. We realized that we had gotten the performance that we wanted and have perhaps exceeded it a little bit.
Well done.
It's a good question as to why others hadn't thought of it, but they didn't, and we thought of it first.
Today, aluminum boosts all kinds of motors, from the Space Shuttle to the Tomahawk. But solid rocket engines burn out quickly. Even the biggest boosters will only last for a few minutes. So how does the Tomahawk travel over 1,500 miles on a single tank of fuel? Find out when MegaStructures returns. Now back to MegaStructures.
Weapon system ready. Allow fire. Discharge grade 4-2. Salvo complete.
Missile broached.
As it breaks out of the water, the Tomahawk starts an amazing transformation. Four fins grow from its tail, and an air scoop drops down in front of them. Then a pair of wings flip out like switchblades. The missile jettisons the booster and speeds away at nearly 550 miles per hour. Within seconds, the Tomahawk has mutated from a rocket into an aircraft, which is just how the cruise missile started out. In World War I, artillery was the weapon of choice. But these guns had a range of only 15 to 20 miles. Planes could reach deeper into enemy territory, but they had one weakness. Early planes had no accurate bomb sight and had to fly so low to the ground that they became targets for enemy guns. In 1917, a crack team of engineers gathered in Dayton, Ohio to tackle this problem. Their vision? An aerial torpedo, an aircraft with the pilot removed and a bomb in his place. Inventing genius Charles Kettering heads the team. Elmer Sperry will build the navigation system, and Orville Wright will design the airframe. The very man who had put humans in airplanes would now work to get them out. The result? The Liberty Eagle, nicknamed Kettering Bug. It was a cheap and disposable aircraft, assembled out of a box in 4 minutes using only a screwdriver and a wrench. And hidden inside was 180 pounds of high explosive.
It's quaint looking, but this quaintness is also tied to a bomb that will kill. So it's technology that looks cute, it looks like a toy. They call it the Kettering Bug, which is a cute name, but in reality it's a weapon of war designed to destroy an enemy's capacity to fight. The plan is to send hundreds of these things, maybe thousands of them, for very specific targets that are deep behind enemy lines that are far beyond what artillery can reach and are too dangerous for a pilot to take his bomber or his fighter back in that area.
The first flight tests were a series of comical errors. But then, after weeks of crashes, the Kettering Bug became the world's first cruise missile in 1918. People had been flying for only 15 years, and here was an aircraft that flew without a pilot. It had an autopilot invented by mechanical genius Elmer Sperry. The heart of his machine was a gyroscope, a fast-spinning disc that stayed stable even while the aircraft was in motion. Connected to the steering with pneumatic pipes, the gyro was supposed to make the bug fly in a straight line. That was the theory. But gyroscopes have one big problem. They drift over time. The gyros in the Kettering Bug were no exception. They had trouble staying on course.
They brought dignitaries from Washington, D.C. to Dayton, Ohio to show it off. And it takes off, but it keeps flying. And instead of flying straight for about 1.5 miles like they wanted it to fly, it ends up veering off and starts flying around toward the city of Dayton. Well, this is a top secret weapon. They don't want anybody to know about it, so they all jump in their cars and they start chasing after this thing as it's buzzing along at 50 miles an hour, which trying to chase down country roads around Dayton in 1917 must have been very interesting. It finally goes out and it runs out of gas and crashes into a farmer's field. And the farmer comes out, oh, an airplane just crashed out here, but I can't find the pilot. Well, to maintain the secret, they grabbed a flying suit from the back of one of the cars and said, well, here's the pilot. He jumped out with a parachute. Well, they didn't have parachutes for airplanes at that time. But the farmer believed him and they kept the secret.
Building the Kettering Bug had taught missile builders valuable lessons. But in the end, the grandfather of the Tomahawk never saw battle. By changing from rocket to plane, the Tomahawk increases its range massively. It drops its burnt-out rocket booster and fires up a jet engine that can fly it for 1,500 miles at 550 miles per hour on a single tank of fuel. In the 1950s, such an engine was unthinkable. Jet engines were huge gas guzzlers. Cruise missiles were enormous, too big for a submarine. What missile builders needed was a miniature jet engine. It takes precision to build even a big jet engine. Making them smaller and more precise would be a tall order. In 1964, the solution came from an unlikely place. The U.S. Army had been looking for a way to fly a soldier to the battlefield. Fast-burning rocket technology had failed. Enter the jet belt.
Of course, the concept started with a rocket belt, but you only had about 20 seconds of life. So then the thought was get an air-breathing engine, which will take less fuel, so you could get, with a given amount of weight, you could get much more flight time. But there was a real question about whether you could design an engine this small. It was thought probably you couldn't.
The engineers at Williams International put their heads together.
So the challenge we had was to take an engine actually a little bit larger than this, consisting of about 6,000 parts, and compress it down into a very much smaller part count.
One trick Williams used was to build highly complex parts like turbine rotors out of a single piece of metal. They radically simplified every component until they had an engine with only 600 parts. Weighing in at only 68 pounds, it was small enough to fit on a man's back.
It's pretty exhilarating. It's almost like somebody grabbing you by the seat of the pants and just lifting you up. It's pretty interesting.
Test pilot Bob Quarter loved showing off the new gadget.
I watched Bob fly it. He had very precise altitude control. He flew it in front of our building at one time where we had a big tree and it was in the fall, and he could point to some leaf he was going to pick up. And he did fly up in the tree. This tree was like 60 feet tall. And he went over and picked a leaf off.
The jet belt spawned a series of prototypes that looked more like James Bond than G.I. Joe. But the military lost interest in these magnificent machines. Maybe they realized that on a battlefield, flying soldiers could easily become sitting ducks. The jet belt never took off commercially, but left one important legacy. Its small jet engine was a boon to missile builders. Now they had the technology to make missiles small enough for submarines, yet so powerful they could fly hundreds of miles. Once a Tomahawk enters the cruise phase of the mission, it begins seeking out its target, and the hunt begins. Next on MegaStructures. We now return to MegaStructures. As the Tomahawk cruises towards an enemy's coast, it faces the hardest task of all, flying hundreds of miles without getting lost. Navigation has always been the biggest headache for missile designers, especially during the Cold War, when the targets for U.S. missiles were on the other side of the planet, over 5,000 miles away. Over such distances, a tiny error could add up to a big miss. Accuracy seemed impossible without a pilot. In 1946, aeronautical engineers designed a missile to end the dreaded navigation problem forever. They called it the Snark. This is one of the last remaining Snarks in the world, restored to its former glory by the U.S. Air Force. Weapons technician Jim Oskins used to maintain these missiles.
Oh, boosters and all. Cool.
Oskins hasn't been near a Snark in years.
It's nice to see the old girl in one piece again. Yep, she's pretty nice. It was an extremely ambitious project, considering they were using 1950s technology in the guidance system.
The Snark had a radically new guidance system, which used an ancient navigation aid, the stars. Using a telescope, the missile would track the position of a single star right above its flight path. Once it had locked onto it, the missile found its exact bearing and could correct its course. Nice idea, but Snark was plagued by failures.
What happened with the one I saw was one booster fired and the other one didn't. It got off the launcher, but it just went into the beach. A lot of smoke, a lot of flame, and a lot of people running. Nobody was hurt, fortunately. We were not impressed, I might add.
Star navigation worked fine in the lab, but not on a missile bouncing through the air at 650 miles per hour.
This was one of the first missiles they ever tried to launch out of Cape Canaveral. And since the guidance system was very, very unusual at the time, very, very experimental, they had a lot of failures. And most of them ended up in the ocean right off the coast of Cape Canaveral. So there was a joke going around, they called it snark-infested waters. Instead, which was true. There was no stretch of the imagination there. It was true, there were a lot of them out there.
The Snark was a fantastic failure. The stars were not the answer.
Solution of the problems involved in long-range missiles would need the cooperation of more branches of science than any other project in history.
Missile designers kept looking for the elusive navigation aid. And a team led by Walter Hess found it while dreaming up a truly apocalyptic missile.
Supersonic low-altitude missile, SLAM. It was the most interesting project I ever worked on. It had all the glamour of being an immensely destructive weapon system. It was a wonderful project.
SLAM was designed to fly into the Soviet Union at 3 times the speed of sound and wreak havoc.
It had 16 1-megaton warheads, and it would go to 16 different addresses, ejecting those warheads upward like a seed ejection mechanism, and it would fly so fast that by the time they exploded, it would be out of harm's way. The missile literally glows red because the temperature of the skin and stagnation temperature is over 1,000 degrees Fahrenheit. The shock wave of this massive missile at that high speed at near the ground has a huge effect. All normal buildings that we know would just be knocked over.
But how could a speeding missile navigate between 16 targets many miles apart?
One of our guys, Bill Hallmark, came up with the idea that every piece of ground has got a unique fingerprint.
Using topographic maps, Bill Hallmark and his team translated the valleys and ridges of the landscape into a digital map and uploaded it into the SLAM's computer. They called their invention Fingerprint. SLAM would bounce a radar beam off the terrain it was flying over and compare it to the map stored in its memory. This is how it would zero in on its targets.
Well, we had a configuration of 50 missiles attacking simultaneously the Russian continent. And then each one, of course, would carry 16 weapons. That's 800 1-megaton warheads. You'd literally destroy Russia. In the end, the State Department determined that this would be so upsetting in the balance of terror, it was thought to be wise not to deploy the weapon system. It would just escalate the balance of power one more notch upward. And maybe Russia, thinking this system would come on, would want to deploy some of their missiles before we had it.
The government killed the SLAM project in 1964 and put the fingerprint technology on the shelf. But when work began on the Tomahawk in the 1970s, it was rediscovered and transplanted into this missile, where it works to this day. Radar navigation gives the missile another amazing feature: stealth. As the Tomahawk reaches the coast, it drops down to evade enemy radar. Hugging the landscape tightly, it speeds along at nearly 500 miles an hour, just 50 feet off the ground. It's a truly amazing feat of flying, and all without a pilot. Some would even say no human could possibly match the skill of a cruise missile. Keith Dennison, one of the finest fighter pilots in England, will put this theory to the test. As a chief test pilot at BAE Systems, he's up for the challenge of chasing a cruise missile in a flight simulator. The simulator team at BAE have designed a low-level, high-speed mission across northern England, a tough challenge.
100 feet is low, it's very low, but it's something that we do train to do.
This is what Dennison is up against, the Storm Shadow, a European cousin of the Tomahawk. Dennison will fly a simulation of the Eurofighter Typhoon, one of the most advanced fighter aircraft in the world.
Even if the missile surprises me and gets away a little bit, then I've got the potential in this aeroplane to turn very tightly and get back with the missile again.
Okay, 3, 2, 1, go.
As programmed, the missile suddenly breaks away to the right, surprising Dennison.
Okay, we're going to have to reset that. Okay, 3, 2, 1, go.
The battle of wits begins again. The missile is difficult to follow. It is small, agile, and fast, flying as low as 50 feet above the ground. A mistake at this speed would leave Dennison only fractions of a second to react. There is a real danger he could crash. But his training and experience has taught him to remain calm and focused. He almost makes it look easy. After 3 minutes of high-speed pursuit, the Storm Shadow has still not managed to shake the Typhoon off its tail. On this short trip, the missile couldn't beat the pilot. But it hasn't been easy.
You wouldn't wish to be doing that sort of intensity of flying for very long periods. Certainly not hand flying the aeroplane. It takes a very great deal of concentration to fly at those levels and those speeds. So you would not want to be doing it for a long time, no.
Well, radar navigation in a cruise missile never gets tired. It does have one weakness. It needs geographic features to lock onto. That is why the cruise missiles in Desert Storm didn't attack Baghdad head-on. U.S. mission planners had feared their Tomahawks would get lost over the flat and featureless deserts of Iraq. So instead, they chose to fly them the long way around over the Zagros Mountains of Iran. Once the Tomahawk zeroes in on its target, it will strike with extreme precision. But how does it know exactly when to attack? Find out when MegaStructures continues. You are watching MegaStructures on the National Geographic Channel. In 1944, an unknown flying object attacked London. Mysteriously, it seemed to know exactly when it reached the city and just fell out of the sky. The German V-1, the so-called buzz bomb, was designed to terrorize Britain.
London is doomed, said Dr. Goebbels.
Well, Londoners wonder what had hit them. A U.S. officer is busy finding out. Hap Arnold had worked on the Kettering bug, the world's first cruise missile built 26 years earlier.
Hap Arnold went to London right after the D-Day invasion, and while he's staying on the suburbs in a house on the southwest part of London, about 5:30 in the morning, the first buzz bombs come over, and he's awakened by them going off, and they're hitting about 1.5 miles from where he's staying. Later in the day, he takes the opportunity to go out and actually visit one of these buzz bomb sites. And he goes to the thing, he sees the bits and pieces, and he quickly understands they've taken a bomb and stuck it on the front of some sort of an aircraft.
The tangled wreckage concealed important clues about how this amazing weapon found its target. Hap Arnold collected all the pieces he could find and shipped them back to the U.S.
This is the fuel tank section, right, Joe? Correct. This is what Hap Arnold would have seen, is bits and pieces like this. Actually, he even talks about seeing bits of the nose cone and the wings were pretty much gone, but the tail surface was still available to him. It's always bigger than it looks in the pictures, isn't it?
Yes, it is. With that big dent in the top of it, too.
I guess it hit the ground hard?
Yeah.
From battered parts like these, American engineers began to reverse engineer Hitler's secret weapon. 3 weeks later, they cracked it. The V-1 had a simple yet powerful jet engine, which accelerated it to an incredible 400 miles an hour. But the most important riddle the Americans solved was how the V-1 knew when to drop. A propeller at the tip of the missile turned as it moved through the air. Each revolution was counted by an odometer in the tail section. At a preset mileage, a guillotine cut the pneumatic hoses to the rudder, locking it in position. Two detonators then ejected a set of spoilers, disrupting the airflow under the elevators and sending the V-1 into a steep dive. Called the Doodlebug, the V-1 was only accurate enough to hit a city the size of London. Good enough for the Germans.
Robot bombs damaged or destroyed 800,000 English buildings in 6 weeks. Over 1 million people have been evacuated from the city of London.
The V-1 had to be stopped.
The Doodlebug is coming in at 440 miles an hour, which meant and the Spitfire would only do about 350 miles an hour, I suppose, the maximum. So you would come in at 10,000 feet, and in a screaming dive, you would be brought down, and the radar would bring you down right onto the Doodlebug. So you're coming in, you can say it like that, and actually you would overtake the Doodlebug on the inside by about 100 miles an hour.
The pilots only had a split second to shoot, and if they got it wrong, they were in trouble.
I was stupid enough to come in dead astern and open fire on the thing when I was absolutely dead astern, and the thing blew up and made an awful mess of the Spitfire. So one never did that again. You learned that very quickly.
Terry Spencer tried another angle of attack.
I was intrigued as to whether there was a pilot in the thing or not, or what was flying these things. So I get about 2 feet in and 2 feet below the wing, and I noticed that as soon as I turned the Spitfire up like that, we would find out later on, it toppled the gyro, and then the thing just spun straight in.
The press loved the story. Terry Spencer was nicknamed Tip 'em Up Terry, the man who had destroyed a V-1 with a flick of his wing.
Dramatic films of the guns in action at the height of the terror, spectacular pictures.
Within a few weeks, British defenses got the better of the V-1.
There it is, the flying bomb.
Over half the 8,000 bombs that reached Britain were brought down. The Germans eventually abandoned the weapon. Americans kept trying.
Mass production of robot bombs in American factories, an adaptation of the German V-1.
U.S. engineers tried to turn the V-1 into a high-precision weapon, but they couldn't.
From the launching platform, a robot goes whizzing.
The American robot bombs still missed their targets by over 8 miles. The modern Tomahawk is 1,000 times more accurate. First, it takes a photo of the target area and compares it to a digital photo in its computer memory. Then a GPS signal guides the missile into the target. Once locked on, a Tomahawk hits within an accuracy of 10 yards. Some say it could even fly through a window. But what if the target is invisible, sheltered beneath thick layers of earth and armored concrete? And now, the conclusion of MegaStructures. Cruise missiles may be incredibly accurate, but have one serious problem: hardened targets. A Tomahawk is designed to be stealthy and light, carrying only 1,100 pounds of explosives. That won't do the job if the target is a deeply buried military bunker, as Sidney Alford will demonstrate. Using a scale model, he simulates a missile attack on a bunker built into rock.
In it, I propose to place an array consisting of a military truck and some little chaps.
Alford's detonator mimics a direct missile strike on the surface of the bunker.
Firing! 4, 3, 2, 1. Ah.
A tomahawk exploding on the surface of a bunker is no more than a pinprick.
Crucial point now is what's happened inside the tunnel. And a little bit of dust has fallen off the roof of the tunnel, but apart from that, everyone's standing up in their action positions. How good as new. Since this detonator stroke bomb exploded in air on the surface, there was nothing confining the pressure, so the extremely high pressure of the gases generated by the bomb could simply dissipate in the surrounding air. They gave up their energy in the form of a shock wave, which is what you heard. You heard quite a loud bang.
To pack more punch, a cruise missile needs a bunker-busting warhead filled with heavy metal. As the heavy warhead pushes the missile deep into the target, a smart fuse detects what kind of material it is traveling through. Once it reaches the air of the bunker, the warhead detonates. Now, Alford simulates what a bunker-busting missile can do.
Here's a very similar block of desert to the previous one. This time, however, we assume that the incoming missile was able to penetrate into the rock a substantial distance.
This time, Alford is so confident that he uses only half as much explosive.
Firing. 4, 3, 2, 1. Well, you can see this is clearly a very different effect. First of all, on the surface, I can see no damage at all. If we look here, we can see obvious damage. The tunnel has been almost completely voided. Here's the vehicle in significantly blown up. Chassis ripped, the top's all gone. The little men, can't see any little men. The only way that compressed gas could get out was by crushing its way through the roof of the bunker with devastating effects on the contents of the bunker, which we see.
A bunker-busting warhead can penetrate about 100 feet into the earth and 20 feet into concrete. Now, there truly is no place to hide.
Once before, you could be fairly sure that if you were far enough behind your own lines and you were in a well-protected bunker, you didn't have to worry about being attacked by an individual aircraft. You felt fairly secure. Now, at any moment, a cruise missile can literally come through the window or come down the air duct and kill you.
The modern cruise missile has come a long way from its humble beginnings. But even the smartest weapon makes mistakes.
The Pentagon said this was a chemical and biological weapons plant. It looked, smelt, and appeared to be an innocent factory to produce baby milk formula.
Most cruise missiles rely blindly on intelligence data, which can be wrong.
The cruise missile, once you've taken the decision to launch it, then it might be a significant amount of time before it hits its target. You might want to change your mind, but with most cruise missiles these days, you don't have that option. With a manned aircraft and a pilot, you can launch on a mission, and if the situation in the target area does not meet your brief, then you can not drop, you can come back, and you can go another day.
But there's a new kind of weapon on the scene. The futuristic cousin of the cruise missile, the unmanned aerial vehicle. UAVs are more accurate than cruise missiles, and they can come back. They can fly more than just one type of mission. The Predator, its skin covered in bulletproof Kevlar. Its unusual shape making it nearly invisible to radar. Its cameras so sensitive that they can tell if a man on the ground is armed or not. The CIA uses it to take out snipers on rooftops or terrorists in their hideouts. Most amazingly, this predator could patrol the deserts of Iraq, but be controlled via satellite link by a 4-man crew sitting in an air-conditioned room in Las Vegas. The more dangerous the machines become, the more they need human guidance.